Welcome everybody to day number 2. We had a great day yesterday. Today the main topic will be on the astrophysical formation channels of the gravitational wave sources. So the first speaker will be Smadar, and then I'll be talking a bit. Then we have Alejandro, who's not here yesterday, but we will have a chance to talk with him later, and he will introduce himself later. And then Jeff Andrews, who is on this game, will be talking in the afternoon. And then we have the hands-on sessions with Jonah that you listening to yesterday. So again, very exciting day. And Smadar, she got her PhD in 2010, then fellowship at Northwestern. She's then a fellowship and worked at Harvard. And after that, she took up a position as an assistant professor to CLA, and that's where you see this. And she has made great contributions to especially formation, binary black hole mergers and triples and so forth. That's what she's going to talk about today. But no matter what, great pleasure to have you here, Smadar, and we're looking forward to your lecture.
Right, cool. Hi, everyone. I hope you can hear me well, and I'm sorry that this cannot be in person. It's the best that we can do right now, so that's okay. I know also that having a talk that is somewhat remote or online or on video can be really different, and I'll try to make it as engaging as possible. So please feel free to interrupt me, ask questions. It will be a lot funner to all of us. And I also want to ask some of the people on the Zoom if you can turn on your video, so at least will not feel that it's completely empty room. I can see some people in the video, so that's good. That makes me feel much better. Thank you. All right, awesome. So I'll start. And indeed, as thank you for the introduction. And then I want to say that my research covers a wide range of topics. I work on the early universe and the structural formation, all the way to dynamics of black holes and stars and planets. And the way that I see it is that the thing that connects them all is physics, and specifically gravity at different scales. And this is really what I think that astrophysics is all about. We're solving physics problems at different astrophysical setting. And in this talk, I'm going to focus on one astrophysical setting, and I'm going to be motivated by the heart of galaxies, but we will see how it's basically generalized to everything. So I'm just going to use the heart of galaxies as a motivation here, but we're going to see where this whole dynamical channel comes from. And in general, what I'm going to do is I'm going to start by reviewing some of the challenges. So I see that there is a delay. Apologies. So we're going to review some of the challenges that take place with merging black holes. So I was told, sorry, it was too late for me last night. So I didn't, for me tonight, not right now in California. So I didn't stay awake to listen to all the awesome talks. But I heard the cliff notes, and I understood that you guys learned about gravitational waves, and today I'm going to tell you about some of the challenges that happen when we try to merge black holes or other compact objects. So that will motivate us to look to help, and there are going to be different ways to help merging compact objects. And I'm going to talk a little bit about, this is the motivation that I said, about star clusters around supermassive black holes at the center of galaxies, as a way to drive us to understand some physical processes. So I'll describe some interesting physical processes there, and something that I call the eccentric Kozai-Lidov. So while it's divided into 3, we will spend a lot more time talking about some physical processes. And then I'll also talk a little bit about collisions, and we will try to disentangle between different channels. That seems like a lot, and that's because big part of it will be on, this will be Friday for you, Thursday for me. So, right? Yes. So it will be my second talk. And again, please again, stop me at any chance. By the way, I'm writing here some of my collaborators. I really want to highlight my group. I like to work with a lot of people. And here everyone is very professional. You'll see some of their pictures as I'll go along. And this is my group during Zoom time. And they're, trying to be silly over Zoom, trying to make the best of it, as I hope that everyone here will do the same. So gravitational waves, which is pretty cool. I know that you've heard a lot about it yesterday. And indeed, LIGO really changed the way that we sense our universe. We no longer rely on electromagnetic spectrum. We can really try to see it in a different way. And maybe you've seen this before. It was in the news, and maybe you've seen it yesterday as well. Here, this is an illustration of some of the detections that LIGO had. In the y-axis is the solar is mass or solar mass, and the x-axis is arbitrary. So there's nothing really interesting about it. There are lots of things that happen in this plot, but I want to draw your attention to the blue dots. The blue dots represent black hole merging. So here is two black holes that merge to one. I don't know if you actually can see my cursor. Can you at all see my cursor? Cool.
Yeah.
Okay. Awesome. And the first thing that I think that draws attention in this plot is how many blue dots there are, right? So in fact, LIGO estimates that about every 15 minutes, there is a black hole merger in our local universe. And this is pretty impressive. So we will have a few that will merge during this talk. So that's pretty cool. And it was such a surprising discovery. And it's even more surprising in light of the prediction. So going back in time, 10 years ago, way before LIGO made their detections, there were lots of thoughts about what will be the frequency of black hole mergers. And people did not think it will be so often. They did not think it would be such high frequency. In fact, there were some that were willing to say that there will be zero completely. So I want to take you through a heuristic understanding of why people thought it's so hard to really merge black holes. So this is going to be more of a cartoonish type of a thing. And I'm going to describe a recipe of merging black holes. And to have a recipe, what I really need is to start with a chef. And I need to start also with two stars, because we think that these black holes are the end result of massive stars, massive meaning more than 20 or 30 solar mass, depending on the metallicity, that goes through stellar evolution, finish its life with a supernova, and leaves behind a black hole. And I need two. So maybe the first question is whether or not we have binary stars. Are there abundant in our universe, in our galaxy? And the answer is yes. There are abundance in the movies. This is Tatooine. So of course, they're also, we expect them in life. I should warn you, I like to tell jokes. Not very funny though, but I still like to do it anyways. So if you feel the urge to laugh, as long as it's not laughing at me, it will be okay. Right, so I will quantify how prevalent binaries are in our galaxy soon. But for now, let's just take Tatooine as a good example. So we have binaries, and indeed what happens to stars as they exhaust their hydrogen supplies, that they go through midlife crisis. They expand a little bit in the sides as they evolve. And here, this star, as it evolves, I drew it a little bit too close to the other star. And what happens is that they start overlap and eat each other. And we see this. We see this in our galaxy. This is, of course, an artist illustration. But we see stars undergoing this overlapping stage. And that is a problem, because what happened is that they start to eat each other and become one star. And then at the end of the day, I'll have one black hole, which is really not good. Sorry, I see that there is a delay. It's not good because I want two black holes and not one black hole. So the answer might be really simple, right? All I need to do is just draw my stars further apart initially, and then I will let each of them evolve and separately, and I'll get two black holes, right? And then I'm done, right? I will let gravitational waves emission. Now you're all expert in that, right? They will take energy, orbital energy. They'll convert it into waves in space-time. There will be these ripples, and I'll get merger, right? However, calculations that were done prior to LIGO's detection estimated that in order to overcome this, it's called common envelope, this eating phase, I need to have the stars so far apart that as they then go through stellar evolution, so they don't just become larger, they also lose mass, and they have maybe supernova as well. So what happens is that through this mass loss, they become even further apart. And at the end, I get that these two black holes are so far apart that it will take longer than the age of the universe for them to merge through gravitational wave merger by themselves. So that is not good because I want them to merge in my own lifetime. And this what led to the prediction before LIGO made their detections that no black holes will be, or not no, but it will be really hard to merge two black holes. And that's really the heuristic problem that led people to seek all kind of other channels. And I should also emphasize that since then, there were many development in this field of binary stellar evolution that were able to overcome this obstacle. But the trigger is already there. We're now looking for different channels, and it's really interesting because we found so many. One of the popular ideas in the literature is maybe to look at dense stellar clusters, such as globular clusters, and see what happens there. So globular clusters are places that are very, very old. They have lots of stellar remnant, and they're very dense. And what happens there is that, and I see that there is a big delay, and I don't know if you can see the movie. So in the little video there, I don't see the movie moves, and I don't know if people on Zoom see it. If I go through like this, do you see the movie moves a little bit? Nothing?
We do see a little bit.
Nothing. All right, so I'll use one of Johan's snapshots. I don't see it actually coming up either. Oh, here we go. And basically what it shows is that, at least you see me, I hope. So if I have a binary and there is another single coming in, what happened is that there are lots of interactions where I get that these binary are being exchanged back and forth, and in each interaction, the binary or the new binary becomes tighter and tighter and tighter until it merges through gravitational wave emission. And that is very popular. There's lots of works about this, trying to understand exactly what is behind this. And I also want to emphasize that there have been a lot of understanding recently about how exactly this works in terms of analytical understanding and the different statistical outcomes. All right, so that's pretty cool. And it happens because globular clusters are extremely dense. But what if we will look at the densest places that there are, which are the center of galaxies? So the center of galaxies, I need to have, I think, like 3 or 4 seconds, 5 seconds, 6 seconds delay between my clicks and my speech. We'll see how it goes. So we know that almost every galaxy hosts a supermassive black hole at its center with masses between million and billion solar mass. And surrounding these supermassive black holes are very dense environments of stars and stellar remnant. And basically what it means is that when I have any star or even a binary in this place, not only does it feel the supermassive black hole, and this movie you probably don't see, the supermassive black hole gravitational field, but also interactions with many, many, many neighbors around it. Luckily for us, we have a supermassive black hole at our backyard where very detailed observations of both infrared, of mainly infrared, we're able to pinpoint that we have a supermassive black hole of about four solar mass. And I really want to highlight that this was then, this led to the Nobel Prize of 2020 in physics. And I want to highlight Andrea Ghez, my colleague and my friend from UCLA. And here in UCLA, we're still in celebration mode, even though it was announced in the fall, but we're so happy for her. And observations such as the ones that Andrea is doing, really helping understand this very unique place. And they help us understand the conditions, the behavior and the dynamics. And we can understand that it's not, right, we're not special in our universe. So maybe the first question that we want to ask ourselves, if we're thinking about the context of emerging compact objects, are there binaries there? This is a good point to try to quantify binaries in general. So we know that in our galaxy, binaries are prevalent. And right, this is our Tatooine from before. And here you see a plot where we have the fraction of stars with companions as a function of the spectral type. So here is our sun-like stars, and our sun had a 50-50 chance to have a companion. And we can think about it whether or not it's a good or bad thing that we don't have a companion to our star. But more massive stars, like the ones that at the end of the day will form black holes, those, the majority of them, if not all of them, are actually in a binary configuration. So that is very encouraging. But this is in the field in young stellar clusters. And you can say, well, Smadar, come on, we don't know if, oh, and I see that there's something in the chat. I don't know. Someone said, not me. Not me what? Sorry, maybe this is really old chat. I'm sorry. Okay, I'll continue. I'll assume that whoever it is not, it's okay now. So you can say Smadar, but you know what? This is in the field and young stellar clusters, but who to tell us whether or not this is how binaries are formed in the galactic center or in any galactic center whatsoever? So that's a very good question. So let's try to see it. So these are very complicated observations to do, to actually try to pinpoint. Oh, okay, this is about the movie. Okay, thank you. This is a very good question. It's really hard to see whether or not we have binaries there. These observations are very complicated, but so far we actually seen 3, which is pretty cool. And we have many, many candidates. And from this, and estimating the completion problem. Sorry, I'm extremely tired. It's been also a very long day. We can estimate that the binary fraction in the galactic center, specifically for massive stars, can be comparable to young stellar clusters, which I just showed you that most of them, if not all of them, are in binary configuration. We also have some other evidence that binaries are prevalent in galactic center. So for example, we have X-ray binaries, lots of them. And the key here is binaries. So that is very reassuring. Another thing is that we have hypervelocity stars. And that's a good place to talk about a physical process that takes place in the center of galaxies. So in the center of galaxies, when I have a supermassive black hole and there's a binary coming very close in, the binary, if it wanders too close to the supermassive black hole, the tides from the black hole can break the binary. And one member of the binary will stay in a very tight configuration, and one will run away on a very in a high velocity. So the fact that we have hypervelocity stars, or at least some candidates of hypervelocity stars, are evidence that there are binaries present, maybe. Additionally, some properties of the configuration and the morphology in the galactic center itself lead to the fact that we can only explain them by assuming large binary fraction. So all of this together suggests that we should have lots of binaries. Or, as Dr. Seuss said it way better than me, that binaries are here and there and binaries are everywhere. All right, so that's good. So here I have a binary. Here is a 6-second delay of a binary around a supermassive black hole. And the question that we want to ask ourselves, will they merge? So that's a very important question to ask because this is my goal, right? To merge to a black hole somewhere. Now, since I'm looking at such a dense place, we need to quantify how dense the center of galaxies are. So here's the center of our galaxy in this picture. And what I want to quantify, I want to think about our nearest neighbor in our own galaxy. So if I think about our sun, and I think about the closest neighbor, which is Proxima Centauri, which is by the way a triple system. Between us and the closest member, there is nothing, right? This is our closest neighbor. It's about a 1 parsec volume. And if I draw the same volume around the supermassive black hole, we will find 1 million stars there. So just imagine the night sky in our neighborhood if we had 1 million stars between us and Proxima Centauri. This is how dense it is. So we need to take that into account. Now this is where some fun begins. I really like this field because if we really want to help black holes to merge, we really need to consider lots of different physical processes all the time. So this is where some of it comes from, because I really need to take that into account. So here, if I consider this binary around the supermassive black hole, what will happen is that it will interact with lots and lots of things that will fly by, and as time goes by, we'll try to unbind the binary and make it become 2 single stars. And I see that none of the animations work. This is really interesting to see. I think it's the first time I give a talk online when I actually see what the other people see. And that makes me feel that after 1.5 years of giving these talks, it was really a disaster. So I think it will really bad. Okay. All these interactions with the neighbors really try to unbind the binary. And I want to highlight here work by one of my students, Anaya Rose, who generalized this behavior for an arbitrary orbit. And this is a very complicated plot, but I can highlight here the timescale for unbinding versus the timescale that to feel some interactions from the black hole. And the rule of thumb is, as long as I'm inside about 0.1 parsec, most of I can ignore all these very weak interactions that accumulate over time, because the supermassive black hole interaction will win. But I didn't quantify what is the supermassive black hole interaction, and there is a nice question, and I think that there might be some questions in your mind that you're not asking. So let's start with a question that we have here. So there is a question, and Aman, and I'm sorry if I mispronounced your name, says, so is there a way of having merging binary black holes without dense environments? Do binary black hole systems observed by LIGO correspond to dense environment generally? The question is, it's a great question. We don't really know. We have all kinds of thoughts, and that relates to how we try to disentangle. And I will talk about this probably on my next talk, because I will probably not reach this part today. But this is an excellent question, Aman. So I wonder if you'll be willing to ask it again during the next talk. Will you?
For sure, yeah.
Awesome, thank you. But I do think that maybe some of you have some questions in your head, and maybe you're not asking this, and I'll I'll say a question that may pop into your head. And the question might be that a minute ago, or well, it wasn't a minute ago, it was the beginning of the talk, I showed this movie that no one saw, but I showed a snapshot of the movie with a binary that become tighter and tighter due to interaction with other neighbors. And here I'm talking about a binary that become wider and wider due to interactions with other members. And maybe some of you think to yourselves, wait a minute, could you make up your mind already? Which is it? Does it get tighter? Does it get wider? And what's going on? And the answer is that it's both. And it really depends on who wins when I compare the binding energy of the binary compared to the kinetic energy of the cluster, right? So I have a binding energy of a binary, and there are lots of flybys. And if the flybys will come with velocity dispersion, so some average velocity that is larger than the escape velocity when they'll interact with a binary, after a long time, I'll get wider and wider and wider, and then I'll break up the binary. And in those globular cluster scenario that I showed you, they begin tighter. So these binaries are tighter, so they're harder, meaning that they are, that all these interactions with the neighbors will make them harder. And here, remember, I want to start with stars that will evolve as a function of time, will become two black holes, and then will merge with the help of some assistant from outside. So that's a big requirement. So I want the stars, the black holes, or whatever binary, I want it to be wide. And that means that there's a clock that works against me, this clock to unbind. So both of these physical processes work when, depending on where I consider my system. And we always need to ask what system we're looking at, what's this velocity dispersion. It becomes more complex and way, I think, more fun because there are all these extra stuff. All right, so now let's consider a wide binary around a supermassive black hole. And my requirement is that this binary will be stable for a long time. What do I mean by stable? Meaning that they'll be far away from the black hole, so the supermassive black hole will not break them, will not do this Hill process. Remember when I said, or maybe I forgot to say it's Hill process, this binary that comes and wander too close to the supermassive black hole and break it apart? This is called the Hill process, and I want to avoid that. So one way for me to do this, to maintain stability over a long time scale, is to have these two on a tight configuration and orbiting the supermassive black hole on a wide orbit, and that's it. And what I can do is I can write the Hamiltonian of this system. And I already written here a Hamiltonian that has some separation of scales. So it takes into account, so it's rearranging the Hamiltonian. It's taking into account the fact that I have the scale separation between a tight orbit and a wide orbit. And I can recognize different parts here in this Hamiltonian. So the first part that I can recognize, I forgot that there is the 6-second delay, is it's the energy of the inner orbit, which goes, there's some color coding that still is not appearing, I think. Well, it's actually harder for me to see now because it's small. So there's this part here, it's the energy of the inner orbit, and it goes with this inner orbit. So that's the blue one. And then I have the energy, Kepler energy of the outer orbit. That's the red one. And everything here is an expansion in the separation between the inner and outer orbit. And if I set the system correctly, it means that I can do the separation, this expansion, because this ratio is a small number. Now I have a question to the audience. Is there a problem in this Hamiltonian? Do you see something that maybe does not agree with what you've learned in classical mechanics, in Kepler, regular Kepler problems?
So,
Oh, I couldn't hear.
repeat. Could you say it again? angular momentum may not be conserved. Like,
so angular momentum may not be conserved was one of the students' answers in the audience.
All right, so we this is I'm very happy that you raised the point of angular momentum because we're going to talk about this. Total angular momentum of the three-body system has to be conserved because nothing can destroy, right? I've got no perturbations from afar. This is a spherically symmetric system. And I'll remind you, Amy Noether theorem. Amy Noether was an amazing scientist who really changed the way that we understand physics. And she showed that we can use symmetries to understand conservation laws. And she showed us that when we have a spherically symmetric system like this, we will have total angular momentum conservation. So indeed, the individual angular momentum of each system, right? So we're used to having the two-body system. So maybe this is what you meant. Two-body system, we have angular momentum is conserved, but for each two-body system here, the angular momentum may not be conserved, but the total angular momentum is conserved. There is one thing here that is problematic in this Hamiltonian. The Hamiltonian is energy in this case, right? Because this is coming from a conservative potential, and it should be negative, right? The Hamiltonian should be negative. But the Hamiltonian, the usual way to write these things is with a positive Hamiltonian, and I can tell you that that caused a lot of problems in the literature when trying to mesh with other physical processes, and it reduced a minus sign for everything. So as long as you remember there is a minus sign here, that this is the solar system dynamic approach to do this positive. So as long as you remember that there is a minus here, you're safe, but there is a minus here. All right, this system was analyzed, I say solar system, was analyzed by Kozai and Lidov separately back in the 60s, and they looked at solar system objects to try to understand this. They did this expansion, and since they have the separation of scales, and since this parameter here, which is the which represents, this parameter here represents the separation between the ratio of separations of the inner orbit to the outer orbit. And by the way, this is some masses, this m sub n, and this is Legendre polynomials. And this theta is a 3D angle. When Kozai, for example, did this and looked at this Hamiltonian, what he recognized is that what we can do is smash the mass around the orbit, because nothing interesting is happening over short time scales. Over short time scales, these two will orbit their center of mass, and then these two together will orbit the supermassive black hole center of mass, right? And if the supermassive black hole, or the tertiary, is not a supermassive black hole, so they're all together will orbit the three body center of mass. But on short time scales, orbital time scales, nothing happens. So we can smash the mass around the orbit and look at this as two wires, one blue and one red here, interacting with one another.
We have some questions.
Yes,
from the
yes,
audience
yes.
here, so let's
Sure.
go ahead and
Go ahead.
Should I shout really loudly? Can you hear me, Smadar?
More or less. So try, and then if I wouldn't understand, I'll ask again.
Okay. So we established that the binary is quite far away from the black hole, right?
Yeah.
I don't really understand why the inclination angle with respect to the spin of the supermassive black hole is important at such a large distance.
Sorry, I didn't hear the part. So I heard the part that you said we established that it has to be far away, but then I didn't hear the question.
We can try this. Yeah.
we're gonna set this up for now. Just
Yeah.
Okay. Does this work? Hi.
Yeah, yeah, wonderful.
So I wasn't sure what you meant by the angle. Is this the angle of the binary with respect to the spin of the black hole, or is it something else?
This phi or this inclination, there are two different angles. So,
Oh, okay. So
Yeah.
I guess the phi.
so the phi is an angle which is between the two radius vectors. So I have a radius vector that defines the inner binary, and I'll have another radius vector that defines the outer binary. That would be a great place to actually do something on the blackboard, but unfortunately, but there isn't. But we can imagine, you can imagine that I have some arbitrary inertial frame of reference, and I will have vectors to each of these for each of these bodies, and then I can define a radius vector which will be basically R1 minus R2 between these two, right? And that will be Rn, and then I'll have another one between the center of mass of these two and the third one, and that will be my R out. And therefore, I have two radius vectors. They need to be transposed, rotate into a common frame of reference, which I'm going to get to talk about in a second. We usually choose a frame of reference that's called the invariable plane. The invariable plane is chosen such as the total angular momentum will be along the z-axis. We established that the total angular momentum is constant, right? Because the system is spherically symmetric. So this is this phi. So it's a 3D angle. It comes with all the other Euler angles or the Nolli variables, however you want to call them. I'm trying to make people remember stuff from classical mechanics courses. So we call it Euler angles back then. It's very similar. And basically, it's like a series of angles that come with this with this separation. Did that answer your question?
Yeah, I think I misunderstood what phi referred to. So thanks.
Sure.
We have more
My
questions
pleasure.
from the audience because we can try
More
to.
questions? We're gonna. So which one is it?
Yeah, the input should be this one.
Is there a more question in the audience?
Yes, 1 second.
Cool.
Is this working?
Well, the question she's hearing us.
So Smadar, can you hear me when I talk in this microphone?
Yeah.
Okay, great.
Okay, hi, I have a question related to, because the 5, whatever it is, like it's explicitly appear in the Hamiltonian. So the corresponding quantity should not be conserved, right? So is the final total momentum is dependent upon this 3D angle, the phi you told?
This is Legendre polynomials that has this phi. So therefore, Legendre polynomials are spherically symmetric. So they should be fine, right? So the entire Hamiltonian should be conserved, right? Legendre polynomials are spherically symmetric.
Okay.
The phi itself is a combination of different angles. We will meet them soon, so bear with me. But there are different angles that describes each of these orbits in space. And them themselves are not conserved, and they will change as a function of time.
Okay, thank you. That answers my question.
Cool. And then there is a question in the Zoom. There is a hand up, but I cannot see who raises their hand. So maybe you can just unmute yourself.
That was me. So I was just wondering about the part in the blue box. So for this, so to say, inner binary system, you would expect that the black holes are closer together. And I was wondering whether you should expect some major modifications to this if you consider a relativistic or general relativistic treatment of this two-body problem.
Oh, that's an excellent question. The answer is yes. General relativity does make a huge difference. Of course, here, when I say that they're tighter, in physics, we always ask, tight with respect to what, right? It cannot be arbitrary. So tight with respect to the orbit around the supermassive black hole. So this can be 1,000 AU for all I care, right? It's not realistic, but it's, it's in my ideal world when I have only 3, it can be however I want to set it. But you are completely correct. And when I will look at real systems, I will need to take into account general relativity corrections, and they make things more interesting. And I can talk about this more maybe later. You can ask me about this more. I'll be more than happy. Like this is like a whole talk by itself, but I'll be happy to talk about it.
Great, thank you.
Sure. Are there other questions?
I I think there was one quick question about the units in the
Yeah.
last term of this Hamiltonian. About
This one here. So I have G, this is MM, and this is R. So the units should be fine, right? This is unitless. This is unitless. And the units are energy GMM over a length.
Yeah, so there is a mass unit missing in the last term.
No, here, this is M, right?
Yeah,
So
but
this
there,
is-
there is m squared.
So this M has it's a mass factor. So this is M sub N. It will be units of the mass square. It's not missing, it's just there. I didn't write how we write it because it's
Thanks.
disgusting. And then inside of it, it will change the ratio of the masses and everything will change as a function of the multiples that I will take. It will be not only the ratios, it's also how they combine. It will be M minus M sometimes. So it will appear in different ways with all the different multiples. So it's disgusting and I skipped it, but thank you very much for pointing this out. This is units of M squared. Other questions? All right, that's perfect. I really appreciate all the questions. That's awesome. And I know now that you're all awake. And that's good. It also woke me up a lot. So that's awesome. So this system was studied, as I mentioned, by Kozai and Lidov. And Kozai, for example, wrote Hamiltonian like this and smashed the mass around and treat this as two wires. What it means is that we're doing a canonical transformation of this Hamiltonian to a Hamiltonian that eliminates the fast angles that are moving, the fast parameters that are moving very, very fast. In essence, it's like averaging, but you never, ever average over Hamiltonian because it's a no-no in Hamiltonian formalism. So you do a canonical transformation that's called the von Seipel transformation in order to get two wires that interact with one another rather than three-body system. And that is called the secular approximation, where we smash the mass around an orbit and treat this as two wires. Basically, this means that this is constant and this is constant. And the fact that the energies are constant, it means that the semi-major axis of each orbit is constant as well. And all the fun stuff that I'm going to describe comes from angular momentum exchange between the two orbits, right? If I have a supermassive black hole, so indeed this orbit will not change by a lot, but you can think about this when I have just another run-of-the-mill tertiary here, that I'll have the two orbits torquing one another. And all of this comes here in this term. This is where the fun is. So as I said, this is something that Kozai did and Lidov did back in the 60s. And what they found is that if I start with initially high inclination, and we can quantify initially more and why this 40 degrees, so we can ask why 40 degrees is interesting a little bit later if you want, that there's a really nice answer. And they saw that when you start with high inclination, if you're lowish inclination but above 40, you're very eccentric like this orbit. And if you're high inclination like 90, then you're more circular. So there is this oscillation between circular orbits and eccentric orbits. So you're trading eccentricity for inclination. And they found that there is this z component of the angular momentum, where the z, remember, is along the total angular momentum because it's conserved. And they can write this, we can write this like that. There's a square root of 1 minus e squared times cosine I. This part here is angular momentum, and this is what we get when we project it, and that is constant. And we can see these oscillations, less inclined, more eccentric, more inclined, less eccentric. What I want to show now is that I want to ask, is it constant? And for that, I'm going to examine a general system, so a general three-body system, basically two-wire system, and I'm going to try to understand whether or not this system is constant or not. So here is my two-wire system or three-body system. They have their corresponding angular momenta in blue and in brownish or reddish. just like our system before. And what I'm going to do is I'm going to just add two vectors, the two angular momenta together, and I'm going to see if it's constant or not. So remember that I can write angular momenta or angular momentum as square root of 1 minus the eccentricity square. Remember, eccentricity, if it's very eccentric, then it's going to 1. If it's circular, then eccentricity of 0. And therefore, if I have eccentricity of 1, it's a radial motion. I have 0 angular momentum, which is what is written here. So if I want to add the two vectors, I can write this as L tot equal to L1 plus L2. And I can recognize, remember, this is along the z-axis, and I can recognize the two angles. I can recognize the angle, the inclination, I1 and I2. So these are defined between the two angular momenta. So I have the inclination of the inner orbit, I1, and the inclination of the outer orbit that comes along with each of the angular momenta. And therefore, I can define the z component of each angular momentum for the inner orbit and for the outer orbit. And we get a cosine I as a present whenever we do a projection, right? So cosine I1 here, cosine I2 here. And we see this is L1 sub z, for example. This is one of quasi constants. They're called quasi constants, right? This is what he said that is constant. And also, he also said that this is constant, the L2 sub z is constant. And this is what I'm going to show you. So it's I'm just going to give a spoiler of this movie. It's not. So let's see what's happening. So what I'm going to do is I'm going to rearrange the stop equation of L tot equal L1 and L2. I'm going to move L2 to the other side, and it's equal to L tot minus L1. Right, so outer equal to total minus inner. And then I'm going to take the square of this. So I'm going to get L2 square, so the outer angular momentum square, equal to L tot square plus L1 square minus, and here I have a scalar product, so I get cosine I as a present, whether or not I wanted it or not. And I can recognize this is the part, this is exactly L1 sub z, right? This is what Kozai said that is constant. So here is Yoshidi Kozai. He died a few years ago, unfortunately. He wrote his paper in '62. There is a story behind it. So Kozai sat in a conference and heard Mikhail Lidov give a talk about his work, and where he basically presented the three-body system, the hierarchical, everything that I just described. And then Mikhail's Lidov's work was published in Russian, and this was in the '60s, and there was there were not very nice relationships between the US and Russia at that time. And Yoshidi went back to the CFA where he was a researcher back then. We did not overlap, I'm not that old. And it was another one of my bad jokes. And he wrote this paper. The Kozai's paper, the seminal paper, is very clear. It's really clear to see. He used Hamiltonian formalism unlike Lidov. But what he found, for example, he expanded the separations there, right? So we can relate the separation to semi-major axis ratio. He expanded to the semi-major axis ratio to the power of 6. He then truncated it to the lowest level of approximation, which is called the quadrupole approximation, which is the semi-major axis ratio to the power of 2. And then he found the following. He found that the outer orbit angular momentum is constant. L2 is constant. So let's think about this for a second. What does that mean? It means that we have symmetry for rotation. Again, Amy Noether comes to the rescue. That means that the inner orbit does not know if the outer orbit is pointing this way or this way. And that should raise a huge red flag to the use of the quadrupole approximation. That basically means that the quadrupole approximation is not good enough, because of course we should the inner orbit should care where the outer orbit points at. So there is a huge problem here. In order to overcome it for this slide and the next, what I'm going to do is I'm going to assume that the outer orbit is circular and it's carrying most of the angular momentum with it. So I have an axisymmetric potential. If I have an axisymmetric potential, I can work with a system that has symmetry for rotation. So fine. So for just now, let's assume that the outer orbit is circular, axisymmetric. Therefore, I can use this system. We also found the famous quasi constant that L1 sub z, L2 sub z is constant. And he found that the only thing that is changing is the angular momentum of the inner orbit. Just to remind you, Hamiltonian formalism. In Hamiltonian formalism, if you want to know if some momentum is constant or not, you need to find the action variable, the angle, and you ask yourself, is the conjugate momentum is constant? So basically it means that if my Hamiltonian is a function of this variable, and I see it, right, like this, that means that the angular momentum is varying. So here I have this little omega 1, it's called the argument of periapse, and 1 for the inner orbit. And basically it tells me where the ellipse points at the frame of the ellipse. So I don't know if you see me very well, but at this point, usually in person, I do a little dance. But the idea is that here is an ellipse. My head is the angular momentum, and the argument of periapse tells me where the ellipse points at the frame of the ellipse, at the plane of the ellipse. And from this little dance, pseudo dance, you can imagine that the conjugate angular momentum is the conjugate momentum is the angular momentum. And there is a color coding. So little omega 1 is blue and L1 is blue as well, right? So Kozai in his process found only omega 1. So he concluded that all these are constant because he didn't found their action variables in, and he only found this one. So now I'll ask you a question. Is there a problem then if I go back to this equation of this L2 square? Is there a problem with this equation given everything that we see that Kozai found? Yes. Again, someone is raising their hand in Zoom, but I cannot, it doesn't show me the name, I'm sorry. But go ahead.
Yeah, sure. Well, we know that the total angular momentum is conserved. And we know that L1z is conserved, and we know that L2 is conserved. So it implies that L1 should be conserved also.
Exactly. Excellent. That is the problem, right? L tot is conserved. L2 is conserved because I also says that L sub z is conserved. And then if only L1 is changing in time, this equation is invalid. And all I did is just adding vectors, right? I didn't do anything here. This is not a real equation. Well, it is, but it's, it's not very complicated. All I did was just adding some vectors, taking the square, and I got something that doesn't make any physical sense. That alludes to the fact that there is a fundamental problem in everything that is happening here. And the problem is that this is not the Hamiltonian. The Hamiltonian has two angles that are missing in it. And it's big omega 1 and big omega 2. And these big omega 1s they're called the longitude of ascending nodes. And they're basically an angle, and now I'm dancing again, outside, it's funny to dance in a chair, but outside the plane of the ellipse. And it tells me something about how the ellipse is tilted, 3D tilt, like this. And I hope that by saying the word tilt, I semi-convince you that the conjugate momentum that comes with this is the z component of the angular momentum for each of them. So here I have big omega 1 in purple, goes with L1 sub z, and big omega 2 in red that goes with L2 sub z. And the reason that Kozai said that the Hamiltonian does not depend on them is because if we work in the system where the total angular momentum is conserved, and I go along the z-axis, then I get that they are constant, and if they are the z-axis, they're equal to exactly pi. So you just plug them in and concluded that these L sub z's are constant. But that's a huge no-no. It's actually similar to taking df dx at x equal 2 and substitute x equal 2 before doing the derivative. So it's a little bit unfair to say it because this has many parameters, and this is a really disgusting Hamiltonian, but basically it's that error. And if we correct this, we get that the L sub z 1 and 2 are not conserved, and this equation then makes sense. And Dan, may I ask, how long do I have?
I would say another 10 minutes.
Oh, okay, wow, awesome, thanks. So then this equation makes sense, and we found that basically this conservation law only makes sense in one specific system. It's only if I have an axisymmetric potential, but only if one of the members is a test particle. And if you think about this, the only conservation then is actually the z component of the angular momentum, and total angular momentum is not conserved. So we re-derived it all. We deriving this equation means that we allow the z component of the angular momenta of both the inner and outer orbit to change already in the quadruple level. So there have been changes already there. And then we went to the octuple level. Remember that I had all these worries about this quadruple that goes like the same major axis ratio to the power of 2. I said that it's a big problematic thing because the angular momentum of the outer orbit is conserved. That is still correct. It's still conserved. It's conserved as it's an artifact of the expansion. But we need to go to the next level, which is the same major axis ratio to the power of 3. And this is where things are interesting. This is called octuple. By the way, this was done before us, this expansion. It was also done correctly. But I think the idea that this z component of the angular momentum is conserved was so well rooted within the community that they've missed that there is everything that I'm going to show you is there. And what it means is that we can tap to large parts of the parameter space, and that the system is really rich and chaotic, far more than was thought of before. And in essence, we can flip an orbit from below 90 degrees to above 90 degrees. And we can also reach extreme eccentricities that are really relevant for us when we want to merge two things. So I don't know if my movies will work at all. We can give it a very short try. I see something lagging and jumping around in the video. Let's jump these movies. These movies show different regimes of cosi, and to try to see how complicated it is. Let's see it here. I'm showing a different system. Here we see the inclination. Remember, this is the angle between the two angular momenta. I'm showing 1 minus the eccentricity of the inner orbit. And I'm showing 1 minus because I want to look at the pericenter passage, how close the system comes, right? I care about that as a function of time. This is a system, by the way, near the supermassive black hole. And we can see here something similar to what Kozai said, right? We're going these oscillations between inclination and eccentricity back and forth. But we can see here the inclination is below 90 degrees, and here is above 90 degrees, and here it blows again. And in general, if we compare it to the standard, the 60s calculation, the blue will come in a second, we can see that it's really qualitatively different. So there is a qualitative difference between the behaviors that was assumed to be and the behavior that it is. Now I write here GR effects here and here, and I remember that there was a question about this. I forgot to ask me, I apologize, I don't remember the name. But this is what happens is that we have a precession, and this entire process here comes because of resonances. So if there are questions about resonances later, I'll be more than happy to answer. But GR precession of the nodes, just like Mercury, it moves the ellipse as a function of time. It happens even if I don't have a tertiary, it just happens. And this precession of the nodes, what it does, it destabilizes the resonance, which is a very interesting dynamical phenomena that happens. So it, in essence, what it can do, it can re-trigger a behavior such as this red behavior that we see here back and forth, but it can also suppress this behavior. So it really depends on which part of the parameter space you are. And lastly, I want to highlight, and this was really GR on like very tiny things. And lastly, I want to emphasize these extreme eccentricity peaks here that we can see. And we saw that they are very prevalent. So basically, we saw that high eccentricities is something that happens quite often in these systems. In a minute, in a second, you will see this plot. These are two different studies with former students of mine. Gunsi is now a professor in Georgia Tech. And you can see here that large part, if we focus here, for example, large part of the parameter space, this blue part, reaches extreme eccentricities. So to finish, whether or not they will merge, the answer is yes. And here I'm showing inclination. Eccentricity is 1 minus e, and semi-major axis is a function of time. Red is our calculation, blue is the 60s. This is for two black holes. This is a work that was done by Baomin, one of my students. It includes precession of the nodes that called the 1 post-Newtonian, and also gravitational wave emission, it's called the 2.5 post-Newtonian. And you can see these high eccentricity peaks and the merger. The quadrupole never merged. So this is an example. And what I will leave to talk about next time is what happens if we include stellar evolution to the mix. And I think I will end here and open this for questions if there are.
Excellent. Thank you, Smadar. So let's take one or two questions if that's okay, and then we'll wrap up this session.
So see, there's a question in the chat. There's what is the typical period of the inner rotating around the outer in these examples? That's a very good question. So for example, in this example, let's the example I don't remember, but I remember the other example. So let me go to the other example, which I remember. This one here, for example, the inner orbit is on 10 AU. So the time scale, the orbital time scale is of the order of few years, something like that. And so it's pretty quick. You can see that the modulation here takes place, this cannot be a few years, right? This is 10 solar mass. This is approximately a year. And then the modulation here takes place on longer time scales. And here you can see, and this is from Snaya's work. Let me make it larger so you can see. In this case, we can see the orbital timescale as well in this plot. So you can see that the orbital timescale means that if the orbital timescale is longer than the eccentric Cosine-Lidov timescale here, the EKL, then I cannot really consider anything. It doesn't make any sense, right? If I need to average it. So it has to take place only when we can consider this approximation, only when the eccentric Cosine-Lidov timescale is longer than the orbital timescale. That's a very good question. Dan, how do you want to handle the questions? Should we take now from the audience?
Yes, I have one question. So my understanding is that any merger via this channel has to go through a regime where the Cosine-Lidov interaction is suppressed by the fast Schwarzschild precession, right? So my question is, no?
Not necessarily, no. So I'm really happy that you brought this up because I think there are some confusion in the community about this. What is not plotted here, and I promise I'll put a plot tomorrow. There is the precession, the Schwarzschild precession timescale. But I can start from a point where the initial conditions are such that the energy of the system is that the eccentric quasi-Lidov is faster than Schwarzschild. And then I can arbitrarily become closer and closer. But my initial conditions that were initially the energy that I had in the system allowed me to go through this phase and not be suppressed.
Okay, but maybe my question is still valid. So is there enough time to circularize until the merger, or do we have then eccentric mergers?
That's a very good question. So there's some studies that estimate that you will have some eccentricities, and it really depends on how you begin it. So most of the time in these type of calculations, for example, the ones that Baumin did, we got that they did not end up eccentric. However, you can have eccentric mergers or have retained some eccentricity compared to the isolated binaries if you have less of a strong perturber, if it's not a supermassive black hole. Therefore, the semi-major axis can shrink slightly better compared to the eccentricity. But the rule of thumb is that the timescale for the shrinking of the semi-major axis is most of the time comparable to the timescale of shrinking of the eccentricity. So this system will not result immediately with a high abundance of eccentric mergers.
Okay, thanks.
Sure, that was a good question.
I think we should probably break, but if anyone has more questions, please put them in the Slack, and then hopefully we can look at them in the future and when Smadar joins us again on Friday as well. If that
There was a
sounds good.
question in the chat, so Yi, if you can copy your question to the Slack, then I'll answer it. It will erase the chat, and I'll forget the question.
Great. All right, thanks so much again, Smadar.
Pleasure. Thank you, guys. Enjoy your day. Bye-bye.
All right, let's take 10 minutes and come back at 10:10.